Math 2414, Power Series, Video 5, the Power Series Convergence Theorem. Full disclosure, in the book, the theorem didn't have a name. I gave it a name, the Power Series Convergence Theorem. It's kind of important. But before we get into it, I want to review the three examples we've seen of power series so far. The first example that we've seen, let's see if I can take advantage of some things here in Zoom. Well, that's a pretty uneventful arrow. I wanted it to be a larger arrow. Will you not be a larger arrow for me? No, I can't even change a color. Well, forget that. Just draw it myself. All right, example number one. We have the sum of n factorial times x to the n power as n goes from 0 to infinity. And the convergence of that power series was very limited. It converged at x equals 0 only. Which happened to be the center of that power series, because the x to the n could have been written as x minus 0 to the n. And remember, the center of a power series is the value that's subtracted from the x. So in this case, it converges at its center and nowhere else. In the second example that we saw, the sum of x minus 3 to the nth power over n, as n goes from 1 to infinity, that converged over the interval 2 to 4. We found that interval by setting up the ratio test, taking that limit, which was in terms of x, setting its absolute value less than, or setting that limit less than 1, and solving the resulting absolute value inequality. You might also recall that there's a bracket on the 2, because when we let x equal 2, we got an alternating harmonic series, which converged by the alternating series test. But when we let x equal 4, we got the original harmonic series, which diverges. The third example we saw in the previous video was the Bessel function of order 0, the sum of -1 to the nth power times x to the 2n power over 2 to the 2n power times n factorial squared as n goes from 0 to infinity. And it was a little messy when we set up the ratio test, but we found out that it converged for any value of x. So its interval of convergence was the entire real number line from -infinity to infinity. Now you might be wondering, what other possible intervals of convergence can we get for power series? Well, that's where the power series convergence theorem comes into play. The power series convergence theorem says, consider the following power series centered at x equals a. So here we have our generic function represented as a generic power series. F of x equals the sum from n equals 0 to infinity of Cn times x minus a to the n. Just remember that the Cn represents some constant as a function of n. Maybe I should say coefficient, but you put in the position number, put in n equals 0, n equals 1, n equals 2, and you calculate the coefficient of x minus a to the n. Oh, by the way, in the previous examples, this was our coefficient function. 1 over n was our coefficient function, and down here it was all this was our coefficient function. It's whatever's not the x to the power. But I digress. When you have a power series, the power series convergence theorem says that there are only 3 possible convergence scenarios, and they kind of mirror the ones that we saw in our 3 examples. The first is convergence occurs only at the center, x equals a. And remember, we always get convergence at the center, because when we put in 0 for a right here, excuse me, when we put in a for x, so if we put an a right there, then that subtraction problem is equal to 0. So 0 to any power is equal to 0. We are using the convention that 0 to the 0 power is equal to 1. In other words, what we're saying is when we put the center in, everything disappears except the first coefficient. So we always get convergence when x is equal to a. But that's only one of 3 possible scenarios when it comes to the convergence of a power series. The second one is convergence occurs for all real numbers. So in other words, instead of having the smallest possible number of values that we get convergence, we get the largest possible number of values. This actually happened in the third example where we got convergence from negative infinity to infinity. So that would be this one right here. So it either converges at a single point, the center, or it converges everywhere, or you get something in between. But we can describe that something in between a little bit more specifically. And here comes the third part of the power series convergent theorem. Convergence occurs on some interval of the form. Actually, let's not type that yet. Convergence occurs on the solution to the absolute value of x minus r is less than a for some real number r. We'll say greater than 0. Actually, it could be greater than or equal to 0, but the equal to 0 is scenario number 1, so we won't worry about that. If you'll recall, and it was a couple of videos ago, but when we were analyzing the convergence of the second one here, we had ended up with an inequality of the form the absolute value of x minus 3 is less than 1. Because the absolute value of x minus 3 is what we had gotten from our limit doing the ratio test, and to get convergence, you have to put that limit less than 1. And then we solved it by sandwiching that between negative 1 and 1, and then adding 3 everywhere to get 2 is less than x is less than 4, which normally as an interval would invoke parentheses, but the ratio test does not have is inconclusive if your limit is 1. And the only way the limit would equal 1 is if that absolute value were equal to 1 in this case, and the solutions to that are x equals 2 and x equals 4. So whenever you get an interval that's not everything, you have to check the endpoints as well, which I'm about to write over here as soon as we get rid of all that. Guess I don't have to, but I'm going to. All right. So let's go back inside the text box. All right, convergence occurs on the solution to absolute value of x minus r is less than a for some real number r. Let's see. This gives an interval of convergence of, let's see, it's going to be a minus r comma a plus r. Convergence at the endpoints, in other words, at x equals a minus r or x equals a plus r, needs to be investigated separately. Now, don't let the a's and the r's throw you off. All we're saying is that you're going to solve some absolute value inequality. You're going to get an interval. The interval is going to be centered at a. If you were to think about this interval down here from a minus r to a plus r, a is the middle, r represents the distance you go in both directions. If you go to the left, you go to a minus r. If you go to the right, you go to a plus r. So what this power series convergence theorem is saying is you have 3 scenarios for convergence. A, you only converge right at the center, right here, and nowhere else. B, you converge everywhere on the whole number line. Or C, and this is the third part, you converge on some interval that is centered at the center, hence the name, by going the same distance to the left and the same distance to the right. That distance is called the radius of convergence. Now, if you already have the interval of convergence like we did back here from 2 to 4, it's easy to locate both the center and the radius. The center is just the average of the endpoints. If you average 2 and 4, you get 3. And the radius is how far you would go to the right or to the left. So we would say that the interval of convergence here is centered at 3 and has a radius of 1. Now that alone doesn't describe the convergence interval because it doesn't address what happens at 2 and at 4 like this does. Excuse me. Don't worry, I'll be using these words in context a lot in the following examples. All right. So that's all the power series convergence theorem says, is that if you have a power series, there's only three possible convergence scenarios. Number one, it converges at the center and nowhere else. Number two, it converges everywhere, no matter what x equals. And number three, and this is the one that always takes more work, it only converges on some finite interval centered at the, centered at the center, with some finite radius that stretches out to the left and right of the center. But when that happens, you also have to check convergence at each endpoint individually, since the ratio test is inconclusive when your limit is equal to 1. All right, let's take a look at a few more examples, because this is really the gist of the entire section.